Have you ever paused to wonder about the fundamental blueprints of our universe? I mean, what if, at its very core, the existence of forces, like electromagnetism or the forces holding atoms together, isn't just, well, a coincidence, but a kind of mathematical necessity?
That's a fascinating way to put it.
Today, on the Deep Dive, we're taking a journey into a concept that's as elegant as it is profound: gauge theory.
It really sits at the heart of modern physics.
Right. Our mission is to cut through the jargon, dive into the sources we've pulled for you, and really uncover how this incredible framework reveals the surprising power of symmetry in explaining, well, the very fabric of reality.
Looking forward to it.
Okay, let's unpack this then. When physicists talk about symmetry, what exactly do they mean? How does it help us understand things?
Well, at its most basic level, symmetry in physics means that certain changes, certain transformations, leave a system or maybe its description unchanged. Think of it like rotating a perfectly round ball. It looks the same after you rotate it.
Yeah.
In physics, it might mean, say, if you shift your entire experiment 5 feet to the left or wait an hour to start it, the laws governing it, the physics, they still hold true.
Right. Same laws apply.
Exactly. A good example is maybe describing fluid flow. If you globally rotate your coordinate system, like turn your map clockwise by 90 degrees everywhere, the specific numbers you use for velocity at each point will change, sure. But the actual physical flow, the way the water's really moving, that hasn't changed at all. That's a global symmetry.
Yeah.
The same change applied everywhere, universally.
Okay, so a global symmetry is like everyone deciding to, I don't know, use meters instead of feet. The numbers change, but the physical distance, the reality is the same.
Precisely.
But gauge theory takes this idea much, much further, doesn't it? It introduces this thing called local symmetry. What makes that so different and, well, so much more powerful?
Ah, yes. That's where the real magic, and frankly, the real demand of the theory comes in. With local symmetry, you're not making the same change everywhere simultaneously.
Okay.
Instead, the parameters of your transformation, how you're sort of adjusting your mathematical description, can vary independently from one point in space-time to the next.
Whoa. So not just one shift for everyone, but potentially a different shift at every single point.
Exactly. Imagine having like a slightly different measuring stick at a different clock at every single location and moment in time, and yet somehow the fundamental laws of physics still have to look the same in your description. It's an incredibly strong constraint to impose.
That sounds difficult.
It is. What's fascinating here, though, is that this is actually somewhat analogous to how we handle physics in a non-inertial reference frame, a frame that's accelerating or rotating.
Right, like being in a spinning car.
Exactly. Those situations can introduce apparent forces, like the Coriolis effect that affects weather. Local symmetry, it's kind of like saying, our description of physics must hold true no matter how we choose to set up our local coordinates or perspective at each point.
So it's not just shifting the whole grid. It's like allowing the grid itself to warp and twist differently at every intersection, but the underlying rules still work.
That's a good way to visualize the abstract idea.
You sometimes hear this called a redundancy in the description. It really reminds me of general relativity, actually, where you can use different coordinate systems to describe the exact same curved space-time. Is there a connection?
Oh, absolutely. There's a deep conceptual parallel there. Both gauge invariance in particle physics and what we call dehomorphism invariance in general relativity, which is that freedom to choose your coordinates. They're both fundamentally about this kind of redundancy, meaning many different mathematical setups can describe the exact same physical situation. And for a theory to be truly fundamental, it needs to handle that flexibility, that redundancy. It shouldn't depend on one specific way of writing things down.
Okay, that brings us to why demanding this local symmetry is just so profound. If we insist that our physical laws stay the same under these, well, frankly, wild point-by-point transformations, something has to give, right? Something has to happen to make it work.
Precisely. You've hit the nail on the head. If you demand local invariance, something must step in to, let's say, compensate for those varying transformations across space-time. Otherwise, your equations just wouldn't remain consistent.
And that something is?
That something is what physicists call the gauge field. Think of it like a connector field. And crucially, these fields aren't just, mathematical tricks to make the symmetry work.
They're real.
They become an essential physical part of the description itself. They are, in a sense, the universe's elegant compensating mechanism. And their inherent field strength, you can think of that like their curvature or intensity, is generally not zero. This means they have real, measurable, physical effects. They are tangible.
Okay, wow. So here's where it gets really interesting for me. This is basically the birth of interactions. Yeah.
Exactly. That's the deep insight.
So imagine you start with a really simple system, maybe some basic particles, just sitting there, not interacting at all. They just exist.
A free theory, yes.
Now, if you take that simple system and you insist that it must also obey local symmetry,
Uh-huh.
the mathematics itself forces you to introduce these new things, these gauge fields, to keep the symmetry intact.
Correct. You have no choice if you want local symmetry.
And as a direct consequence, it just falls out of the math interaction terms automatically appear in the Lagrangian, which is, the system's blueprint. It tells everything how to behave.
That's right. The interaction terms are required by the gauge principle.
And the little bundles of energy of these gauge fields, the quanta, those are the gauge bosons.
Yes, the force carriers.
And these are the particles that mediate the fundamental interactions. So things like electromagnetism, they don't just exist separately, they naturally emerge, they arise from this fundamental demand for local symmetry. It's kind of mind-blowing.
It truly is one of the deepest principles we've discovered about nature. And this idea, while it seems almost obvious in retrospect, had quite a winding journey through history.
Oh, right. It wasn't just discovered overnight.
Not at all. The actual term gauge theory and the first specific, though ultimately incorrect proposal came from Hermann Weyl back in 1918.
Weidel, okay.
He was trying to unify Einstein's general relativity with electromagnetism. He imagined an eigenvariance and invariance under a change of scale or gauge. His initial attempt didn't quite mesh with experiments, but the core idea, the seed, was planted.
So what happened next?
Well, it was really after quantum mechanics was developed that Weyl himself, along with others like Vladimir Fock and Fritz London, found the right track. They realized that if you replaced Weyl's simple scale factor with a complex quantum phase factor,
A quantum thing. Okay.
it naturally led to what we now call a U1 gauge symmetry. And this brilliantly explained how the electromagnetic field interacts with the quantum wave functions of charged particles like electrons.
So quantum mechanics was key.
Absolutely. Weyl's 1929 paper really cemented the modern concept, and Wolfgang Pauli was instrumental in popularizing it and understanding its significance later on. It's also kind of amazing to look back and see that hints of this invariance were sort of hiding in plain sight much earlier.
Really? Where?
Well, James Clerk Maxwell's original equations for electromagnetism from the 1860s. They implicitly contain this gauge freedom. And even David Hilbert derived Einstein's gravity equations from an invariance principle around the same time Einstein did. But the deep connection to symmetry as the generating principle wasn't fully appreciated until Weyl's work.
So the idea was kind of simmering, implicit maybe, but Weyl really crystallized it, especially after QM. But the real explosion of its power, the thing that showed how universal it could be, that came later, right, in the mid-20th century.
Exactly. That was the monumental leap made by C.N. Yang and Robert Mills in 1954.
Yang and Mills. Okay, what did they do?
Inspired by Pauli's work on symmetry and quantum field theory, they generalized the relatively simple abelian gauge symmetry of electromagnetism, that's U1, where the order of transformations doesn't matter, like simple rotations. They generalized it to a more complex non-abelian type, specifically SU2 symmetry. In non-abelian theories, the order does matter, like rotating a book in 3D space. This SU2 symmetry was relevant for something called nuclear isospin, a property relating protons and neutrons.
And this Yang-Mills theory, that was the breakthrough.
It was the prototype. It provided the mathematical framework for describing forces beyond electromagnetism, forces where the carriers themselves interact with each other. It was crucial for tackling the puzzles of elementary particle physics.
And the success stories that came from that generalization are just, well, they're the foundation of modern physics, aren't they?
They really are. Yang-Mills theory found its first major success in describing the weak nuclear force, the one responsible for radioactive beta decay. This led directly to the development of the electroweak theory in the 1960s and 70s.
Which unified electromagnetism and the weak force. Incredible.
Absolutely. And then another stunning prediction emerged from these non-abelian gauge theories, something called asymptotic freedom.
Asymptotic freedom. What's that?
It means that the strong nuclear force, the one that binds quarks together inside protons and neutrons, behaves strangely. It actually gets weaker at very short distances or high energies, and paradoxically stronger as you pull the quarks apart.
Wow, that's counterintuitive.
It is. But it was exactly what was needed to make sense of experiments probing protons. This concept was key to formulating quantum chromodynamics, or QCD, the theory of the strong force. QCD uses the SU3 gauge group to describe the color charge of quarks.
So let me see if I've got this. Electroweak theory for EM and weak forces, QCD for the strong force.
Mhm.
What does this all add up to?
It adds up to the standard model particle physics, the absolute bedrock of our current understanding. The standard model is fundamentally a gauge theory,
The whole thing.
the whole thing. It elegantly unifies electromagnetism, the weak force, and the strong force under this single beautiful gauge principle, using that combined symmetry group, U1 times SU2 times SU3. It describes almost all known particles and their interactions, except gravity so far.
Amazing.
And it's worth mentioning, the impact wasn't just contained within physics. The deep mathematical structures inherent in gauge theories, particularly Yang-Mills theory,
Mm.
they've had a tremendous, almost revolutionary influence on pure mathematics too.
How so?
Well, starting in the 70s and 80s, mathematicians like Michael Atiyah, Simon Donaldson, and others realized that the equations from classical gauge theory held profound insights into the geometry and topology of abstract spaces, especially four-dimensional manifolds. This led to breakthroughs in math, new invariants, connections between physics and geometry, work that earned Fields medals and is still incredibly active today. It shows how fundamental these ideas really are.
Okay, let's maybe bring this back down to earth a bit. Can we connect it to some more familiar physics? You mentioned electromagnetism.
Sure, think about classical electricity and magnetism. You often describe it using potentials, the electric potential V and the magnetic vector potential A.
Right, V and A. I remember those.
Well, there's a funny thing about them. You can actually change them. You can perform a specific mathematical tweak called a gauge transformation, like adding the gradient of some function to A and adjusting V accordingly.
Okay.
And when you do that, the actual physical, measurable electric and magnetic fields, the E and B fields that exert forces, they remain completely unchanged.
Ah, so the description changes, V and A, but the physics, E and B, doesn't.
Exactly. That's a perfect, tangible example of gauge symmetry right there in classical physics. Your description has some freedom, some redundancy that doesn't affect the physical reality.
Cool. And then in the quantum world.
Then you get quantum electrodynamics, QED. It's really the simplest and arguably the most stunningly successful physical gauge theory we have. It's an abelian gauge theory based on that U1 symmetry group we mentioned.
The one Wheel figured out.
That's the one. Its gauge field is essentially the electromagnetic 4 potential, combining V and A, and its gauge boson, the force carrier particle, is the photon, the particle of light.
And the gauge principle tells you how photons interact with electrons.
Precisely. The requirement of U1 gauge invariance naturally dictates the form of the interaction, what's called minimal coupling, between the electromagnetic field and charged matter fields like the electron field. It just falls out.
Okay. And then building on that, the standard model is the big non-abelian version.
Right. As we said, its specific gauge group is U1, S22, X, U3. This structure directly gives rise to the 12-gauge bosons we know mediate the forces.
12. Let's see. The photon for EM.
One photon, yes. Then 3 massive weak bosons, the W plus W and A, and the Z boson for the weak force.
Okay, that's 4.
And 8 distinct types of gluons for the strong force, carrying the color charge between quarks.
8 gluons. Wow. So 1 plus 3 plus 8 plus 8 was 12. Got it.
And the principle might even go further.
Mm.
As we touched on, general relativity, our theory of gravity, also has these gauge-like symmetries that diffeomorphism invariance, the freedom in coordinates.
Right.
And many of the theories trying to unify gravity with quantum mechanics, theories of quantum gravity, they actually postulate the existence of a graviton, a particle that would mediate gravity, as a gauge boson itself, suggesting maybe this gauge principle could eventually encompass all the fundamental forces.
Surely unifying idea.
It seems to be. But while classical gauge theories are beautiful and powerful, trying to make them quantum mechanical, the process called quantization isn't always straightforward.
Ah, okay. So there are some hurdles when you go quantum. Why is it tricky?
Yeah, it raises some important, quite technical questions. It's largely due to those very symmetries, the gauge constraints inherent in the theory. They introduce subtleties and mathematical complexities when you try to move from a smooth, classical description to the probabilistic, fluctuating world of quantum mechanics. You have to be careful about redundancies and ensure you're only quantizing the true physical degrees of freedom.
And it's in that quantum realm that we run into these really intriguing, almost paradoxical things called anomalies, right?
Exactly. Anomalies are fascinating. They occur when a symmetry that seems perfectly valid in the classical version of the theory gets, well, broken or violated when you incorporate quantum effects.
So a symmetry that should be there isn't once you account for quantum stuff.
Pretty much. For instance, there's something called the scale anomaly. Classically, some theories might look the same at all distance scales, but quantum effects can break this,
Yeah.
leading to things like a running coupling constant.
Running coupling constant. That's like the strength of a force changing with energy, like asymptotic freedom in QCD.
Precisely. Asymptotic freedom is a direct consequence of the scale anomaly in QCD. Then there's the chiral anomaly, which involves symmetries related to particle handedness. This one connects gauge theory to deep ideas in mathematical topology, things called instantons, and it has very real-world consequences.
Like what?
Like explaining, for example, the observed decay rate of a particle called a neutral pion into two photons. The chiral anomaly is crucial for getting that calculation right in QCD.
Okay, but then there's the gauge anomaly, and you said this one is absolutely critical. If this kind of anomaly must cancel out for a theory to make sense physically, what does that tell us? Does that requirement actually constrain the universe?
It absolutely does.
Mm.
And this is perhaps one of the most profound implications of studying quantum gauge theories.
Hmm.
A gauge anomaly, an anomaly in the fundamental local symmetry itself, would render the theory inconsistent. It would break down, predict nonsense, like probabilities greater than 100%.
Hmm.
So for any physically realistic gauge theory, like the standard model, all potential gauge anomalies must cancel out completely.
Okay, they had to vanish.
So here's the kicker.
Yeah.
Within the standard model, specifically the electroweak part, U1, SU2, if you calculate the potential gauge anomalies arising from all the known fundamental particles, the quarks and the leptons,
Mm-hmm.
you find that they only cancel perfectly if the number of quark families is exactly equal to the number of lepton families.
Wait, seriously, the math demands that.
Seriously, the internal mathematical consistency of the gauge theory itself requires this specific balance between the fundamental building blocks of matter. It dictates that for every type of lepton, like the electron and its neutrino, there must be corresponding types of quarks, like the up and down quarks. It's an astonishing prediction, derived purely from the mathematical structure, that matches exactly what we observe in nature: 3 families of quarks and 3 families of leptons.
That is incredible. A deep mathematical rule dictating the particle content of the universe.
It's a powerful example of how demanding symmetry, especially local gauge symmetry, isn't just an aesthetic choice. It imposes incredibly tight constraints on what a fundamental theory of nature can look like.
Wow. Well, what an incredible deep dive we've taken today. We went from this fairly simple, intuitive idea of symmetry
Right, something we see all around us.
all the way to seeing how demanding a local version of that symmetry leads us to this intricate, powerful mathematical framework gauge theory that literally underpins our entire understanding of the fundamental forces.
Indeed. And it's crucial to remember, gauge theory isn't just some abstract mathematical game. It is, as far as we know, the precise language the universe uses to describe how particles interact, how forces work, how everything is held together.
It's really an amazing testament to how these deep mathematical principles seem to not just explain, but actually dictate physical reality, predicting the existence of the forces and particles we see.
Absolutely. The predictive power has been phenomenal.
So here's something for you, our listener, to ponder. Consider how this seemingly abstract demand, this insistence on local invariance in a mathematical description, can cascade through the logic of gauge theory to predict the very existence of fundamental forces like electromagnetism and the nuclear forces, how it predicts the particles that carry these forces, the gauge bosons, and how it even dictates this fundamental balance between quarks and leptons in the cosmos. It really makes you wonder, doesn't it? What other, perhaps even deeper, unseen symmetries might be out there, shaping our reality in ways we haven't even begun to uncover yet?